Hello, this is Mason Haggerty with question 12.6 from the Fundamentals of Heat and Mass Transfer by Bergman. This question states, consider a small surface of area A1 equals 10 to the negative fourth meters squared, which emits diffusely with a total hemispherical emissive power of E1 equals 5 times 10 to the fourth watts per meter squared. We can see the diagram here with A1 oriented in the N1 and A2 oriented with N2. The difference from N2 to the line of separation is theta 2 equals 30 degrees for A2, and theta 1 equals 60 degrees for A1, and the separation distance is R2 equal to 0.5 meters. So part A says, at what rate is this emission intercepted by a small surface area A2 equals 5 times 10 to the negative fourth meters squared, which is oriented as shown. B says, what is the irradiation, G2 on A2? And C says, for zenith angles of theta 2 equals 0, 30, and 60, plot G2 as a function of the separation distance for 0.25 to 1 meter. So to begin our assumptions, we are assuming both surfaces are opaque, we are assuming that they are diffuse, we are assuming that they are gray, we are assuming that there's no interfering medium, and we are assuming that A2 over R2 squared is much less than 1. So to begin, we can look at equation 12.11 from the textbook that says dq is equal to I, which is a function of lambda, theta, and phi, dA cosine theta d omega. Because we're going from 1 to 2, we say that q1 to 2 is equal to I, and because we are assuming that it is diffuse and it is not reliant on wavelength, we are saying that it's just I, which is a function of theta and phi, which are both angles. Area 1 cosine of theta 1 and d omega 1 to 2. If you look at equation 12.15, we can see the fully expanded integration there, but we don't actually really need to do anything with that because we know that from equation 12.16, E of lambda is equal to pi I of lambda, and so we can rearrange this and see that I is equal to E1 over pi, and so basically you just plug this back into the previous equation before that full integral, and you get that Q1 to 2 is equal to E1 over pi A1 cosine theta 1 d omega, but because we know that d omega is equal to, or roughly equal to, A2 cosine theta 2 over R2 squared, we can plug that in and get that Q1 to 2 is equal to E1 over pi times A1 cosine theta 1 times A2 cosine theta 2 over R2 squared. At this point, we know all these values, so let's just plug it in and solve for part A. So we get that Q1 to 2 is equal to 5 times 10 to the fourth watts per meter squared over pi times 10 to the negative fourth meter squared times cosine of 60 degrees times 5 times 10 to the negative fourth meter squared times cosine of 30 degrees divided by 0.5 meters squared. This gives us a final answer of 1.378 times 10 to the negative 3 watts. For part B, we're finding the irradiation G2 on A2. So for this, we take the Q from 1 to 2 and divide it by the area of 2. So for that, you get 1.378 times 10 to the negative 3 watts divided by 5 times 10 to the negative fourth meters squared, and you end up with 2.757 watts per meter squared. And then for part C, where we have to find or plot the difference for all the 3 zenith angles and the changing R2, I made this little script below. So in this, basically, it just defines the constants that are given, and then it states, it creates a vector for the R, so changing between